Do you have any questions about the last times? Okay, so let us continue. So today I want to continue about the affine algebras. So last time we obtained some realization of affine GLN at the level 1 in terms of free fermions. Namely, it was the algebra generated by currents J alpha beta of Z given by normally order products of fermions, psi alpha, psi star alpha of Z, psi beta of Z. And it satisfies the following commutation relations. So you can write it as OPs of these currents. Maybe let us introduce the generic Lie algebra notation. In a sense, let us call this indices A and B. So, in this commutations relation, where of this form. So, and the OP is this K GAB over Z minus W squared plus FABC and GC of W over Z minus W. And if you write it in terms of modes, and they look like JAN with JBM is delta n plus m0 K delta F GAB plus FABC G C n plus m. So K n. So sorry, K n. So zero modes form the usual Lie algebra, and higher modes commute in some trivial way. So, and if this indices are pairs of are this pair, so then it corresponds to GLN. So GLN hat and the level K. Oh, and the last time I promised that we will be able to write some energy momentum tensor, which will describe simply this algebra. In a sense, it will be the energy momentum tensor for the fields generated from J's. So if some CFT has a affine algebra symmetry, then it has at least some subsector which is kind of a sub-CFT, and it is described by its own energy momentum tensor. Probably it is everything that we have. Probably it is just some sub-theory of a big graph theory. So usually it should be clear from the central charges. If we obtain something with central charge equal to the initial central charge, then it is everything. Well, in the case when we know that there are no subtheories with negative central charges. So today I want to find such an energy momentum tensor And let us study it actually first for some generic Lie algebra, and then see how it applies to Jalen hat and how this produces the original Fermat energy momentum tensor. So. And generic algebra is a little bit simpler because it has a single index which labels its generators. So, so it's simpler computationally. So let us and you can also choose the normalized basis in this algebra, so such that this GAB equals to delta AB. You can always rescale generators in such a way. So the idea to write this energy tensor is simply that T is some kappa times sum over A T of Z plus kappa sum over A T A of Z T A of Z. T A of Z normal product. And I would like to do all these computations using operator state correspondence. Thank you. Yes. Yes. Mm. So first let us remember the definition of this normal product. So normal product of two operators, so in this case of the same operators, G of W, J of W, or maybe, well, let us write J of Z, is the contour integral of this kind, 1 over 2 pi I, dw over w minus z, j of w, j of z. So it simply takes a product of two fields, expands it around the second field, and takes the constant term of this OP. So it drops all singular terms and taking first non-trivial term. And if you want to write it as so it's an integral around z. If you want to write it in terms of modes, we should write this as a sum of two integrals. It is 1 over 2 pi I, the integral over absolute value of z by absolute value of w is greater than absolute value of z minus integral absolute value of w less than absolute value of z. dz over w minus z, j of w, j of z. And so we now expand this 1 over w minus z in powers of z over w, because w is greater than z. So it is the integral dw over 2 pi I, sum of z to the n w to n plus 1 from n equals to 0 to infinity. J of w So here we should actually put a radially ordered product, because it is all this can be done only under the path integral, and path integral always computes a radially ordered products of fields. So if you take this into account, then if absolute value of W is greater than absolute value of Z, G of W is on the left, and G of Z is on the right. And we can also expand this 1 over W minus Z in this way, so that W is greater. And another term is almost the same expression, but with sum from n equals to minus infinity to minus 1 Z n over W to n plus 1 product in the opposite order, J of Z, J of W. Like this, and now let us write the first terms of this integral. Actually, I should have put some label like GA here. So, and let me also write the definition of G of J. So J A of Z is a sum of J A n over Z to the n plus 1 over integer n's. So, taking into account this definition, what are the first terms of this expansion of this integral? So we have something. So this equals to something, some modes times J of Z plus JA of Z, also something else, some different modes. So what modes can appear here? Hmm? Who is n? I'm asking about this particular. Yes. Mm, no, but the main question is what is the range of this summation? What is the first j and so it's jn minus 1. And who is n? So, oh, okay. No, that's I'm asking. So the first j is j minus 1, right? Ja a minus 1. Multiplied by z to 0. And then some positive powers like z, j, a minus 2 plus z squared, and so on. I'm asking because we will need not the general formula like this infinite series. We will need just first few terms of this series. Because for example, I don't want to compute the commutator of this components of J of this ln lm. I want to act on some vector. So, and here we have everything else. So here we have negative j's and negative powers of j, and here we'll have j a0 z inverse plus j a1 z minus 2 plus and so on, right? So there is this expression for the energy momentum tensor, right? And now let us check that this J, these currents JA are actually primary fields for the energy momentum tensor. It is possible only for some special value of kappa. So we want T of Z with J A of 0 be J A of JB JB of 0 over Z minus W squared plus dJB of 0 over Z minus W. Oh, actually, I never tried to do this, but I just realized that probably it might be better to try to compute this OP in the opposite way. In a sense, we can try to act with J B on T of 0. In a sense, there is an equivalent form of this relation saying that JB of Z with T of 0 should equal to plus regular should equal to JB of 0 over Z minus double. Oh, sorry. I wanted to put W equal to 0. Z squared and Z. So here it will be JB of 0 over Z squared. So, in other words, if you pass to this operator state correspondence, it should mean that J B of Z acting on L minus 2 acting on 0 is Z minus 2 L J B B minus 1 acting on 0. or in other words, since this JB of Z contains so since Z minus 2 part of JB of Z is J1, it means that JB1 acting on L minus 2 acting on 0 should equal to JB minus 1 acting on 0. Is it okay? Because if you look at this expansion, then coefficient in front of 1 over z squared is J1. So, that's fine. So, uh, so, if you agree with this, let us proceed to the computation. Okay. So first we need to compute the action of L minus 2 on this vacuum. So we know that the definition of the natural momentum tensor is well. So we know that this is T of z, and L minus 2 is the coefficient near the constant term, because T of z is sum over integers ln over z to n plus 2. So L minus 2 is so it is L minus 2 plus like z L minus 3 plus 1 over z L minus 1 plus and so on. So L minus 2 is the constant term. So let us use this. So T of z acting on this vacuum is JA minus 1 plus z JA minus 2 plus and so on. Kappa sum over A. JA of z acting on vacuum. So this should be taken. So we should take the constant. Yes. So then we'll take the constant term of this plus sum over A J of z JA0 z minus 1 plus JA1 and minus 2 plus and so on acting on vacuum. So this term it just vanishes, right? Because it has positive 0 and positive modes of J. So this is 0. So we are left with that term, and we should find the coefficient near the constant term. So let me maybe also write that term. So okay, L of z acting on vacuum is kappa sum over A ja minus ja minus 1 plus z ja minus 2 plus and so on. And here we have this part which contains negative powers of z and 0 and positive modes of j, which act by 0. And we also have a negative part which survives. It is j, so it is ja minus 1, like actually the same as written here. Z, J, A minus 2 plus and so on, acting on vacuum. So if you are interested in the constant term, which is J, which is L minus 2, we simply take this term and this term. So L minus 2 acting on vacuum is kappa J A minus 1 squared. So there is this vector that corresponds to the energy momentum tensor in terms of smoothie current, sum over A. And in principle, this could be written just from dimensional arguments, because if this index is minus 2, then sum of these two indices should also be minus 2. And if one of them is positive, it acts by 0. If one of them is 0, it also acts by 0, because it is a vacuum. It is invariant under this algebra transformations. So it's the only term that can survive, right? So, any questions about this? So now let us check this equation that it should satisfy. Namely, let us act with J B1. So kappa sum over A J B1 acting on J A minus 1 squared acting on vacuum is we need to commute it with this product of two j's. So it is kappa sum over A J A1 with the J A minus 1 J A minus 1 plus J A minus 1 J B1 J A minus 1. So this acts on vacuum, this also acts on vacuum. So there are these two terms, and now we need to use that commutation relation. So this will contain the first term with n equals 1, so it will be sum over A k delta AB J A minus 1. Let us write it like this. And the next term is when they commute. Yes. So it will be FBAC times J JC0. And then same from the second term. JC0 and also is that term JA minus 1. And here again the first term K delta AB JA minus 1 plus FBAC JA minus 1 JC0 acting on vacuum. So do you see any terms in this expression that vanish immediately? Yes. So this one vanishes, but this one does not vanish. We need to commute them. So it will not contain a sample extension, but it will give some contribution. So here we have kappa 2 kappa k j a minus 1 acting on vacuum plus so we need to write thank you, yes, and that would they be originally. So here we have kappa f BAC times f c a b prime times j b prime prime minus 1 acting on vacuum. Okay, this seems to be correct. So we see that well, so this term will be proportional to delta Kronecker because it is a kind of trace of trace of a product of two representation matrices when we act with this algebra in the adjoint representation. So it will contain some constant that relates a fundamental and an adjoint representation, and it's called so maybe up to a factor of 2. It is called dual Crookes-Tan number. And we will compute it now for GLN. So we can write that this equals to 2, let's call it H check, times delta B prime. So here we have sum over B prime, sum over sum over A, C, and B prime. So actually I should have put here sum of C, A, C, B prime. So this is 2H check times delta Kronecker. And altogether it gives 2 kappa times K plus H check. Times J B minus 1 acting on vacuum. So corollary of this statement is that kappa equals to 1 over 2 K plus H check. H check. In this case, J is a primary field for this energy momentum tensor. So, is it okay? Let us do like this. Now let us compute this H check for SLN. Actually, it will equal to N. We'll see it now. So I would like to see on this. So SLN. It has generators EAB with this commutation relation, like EAB with ECD equals to delta BC EAD minus delta ED Oh, wait, probably I want to do something else. Sorry, let me think. Oh, maybe it's fine. So there is this commutation relation. ADCB. And also, if you want SLN and not a GLN, then another set of generators is A minus E B B. So in particular, they appear when we commute EAB with EBA. This is EAA minus EBB. And now, what this computation is about. So we have some scalar product on this algebra defined in the fundamental representation. So scalar product of A and B is trace of so we are considering the generators with zero trace. So trace of trace of A is zero, so for any matrix, and there is a scalar product in the fundamental representation, which is defined by trace AB. And there is also a scalar product in the adjoint representation. In a sense, we can act with this algebra on itself. So we can send any matrix to its adjoint action, which is a commutator of this matrix. And so such commutators act on the space of matrices. So and A acts on SLN. And we can define another scalar product, like A, B adjoint is a trace of adjoint, a trace over, so here it is a trace over Cn, and here it is a trace over C n squared minus 1, adjoint of A, adjoint of B. So these traces are these scalar products are proportional because there is only one invariant scalar product on the simple Lie algebra, and because if there are two scalar products from more than one, we can combine degenerate scalar product and find its kernel. It will be some subalgebra. So we want to compute this proportionality coefficient between adjoint and fundamental representation. So let us, because this is what we are computing here. We take some, we have some algebra with generators like TA and TB with this commutation on this commutation law. So FABC TC. And this F is completely antisymmetric matrix. So when we compute this expression, we are summing over. So we have two indices which correspond to in this case T and TB, and we take so we kind of multiply these two matrices by the indices A and C, and take trace. So we can write that this matrix is the matrix of action in the adjoint representation. So a trace of adjoint of TA, adjoint of TB, will be TA prime. It will be a sum of f a b c f a prime cb, sum over b and c. So let us now compute this for this SLN. Namely, let us take the generator of this kind. So let us take, because if this matrices are proportional, then it will be enough to compute this trace only for one matrix. Let us take first trace of E11 minus E22 with E11 minus E22. This will be 2. And now let us compute a trace of a square of adjoint action of this matrix. So that's what is right on this matrix. So E11 minus E22 commutator with sum EAB is what? So it makes sense to compute this commutator only if maybe it's actually easier to compute the commutator of this matrix with arbitrary matrix, like with some matrix A. So it is there's a commutator of a matrix of this form, 1 minus 1, 0 everywhere, with some A11, A12, A21, A22. So when you compute with diagonal matrices, it gives nothing. If you commute it with the first row in general, then in one expression it is multiplied by 1, in the other expression is multiplied by 1 from this side. So we have something like this. 0, 2 times A12, here it will be A13, A14, and so on. So here we will have minus 2 times A21. Here it will be 0. Here it will be minus A23 minus A24 and so on. So this block. Here we have just zeros because no this indices coincide with one or two. And here we can write by analogy. It will be A31, A41, and so on. And in this column, it will be minus A 32 minus A42. So we see that all generators of this algebra are eigenvectors for such adjoint action. So a trace of adjoint of E11 minus E22 is just a sum of squares of its eigenvalues. So a trace of adjoint of E11 minus E22, adjoint of E11 minus E22. Sorry. Is 2 squared plus 2 squared plus, let us count the number of these plus ones and minus ones. It is n minus 2 times 2, n minus 2 times 2 plus n minus 2 times 2. So total n minus 2 times 2 times 2, right? So in total it is 4n. So if we would say that this is a trace in the fundamental representation, trace Cn. No, it is fine. We just write them as such matrices. Oh, just all right. Yes. So and therefore the ratio of two scalar products, scalar product in the adjoint representation divided by scalar product in the fundamental representation is so we need to divide 4n by 2. It is just 2n. And since we said here that it is 2 times Coxeter number, a dual Coxeter number, well, this is equal to 2h check. So h check for SLN equals to n. So for SLN, and we should also, yes, so for SLN, we should choose this scalar product such that it is only SLN scalar product. So we can write this in terms of this matrix indices by so we need to write we need to introduce an SLN scalar product. So AB for SLN which is SLN. It is a trace of AB minus 1 over n, a trace of A, a trace of B. In this way, we removed GLN scalar product because scalar product of 1 with any B SLN equals to 0. Right? So, here we should have 1 over 2 k plus n, sum over A, j j alpha beta of the j beta gamma of the or beta alpha of the minus I think 1 over n k plus n sum of j alpha alpha of the j beta beta of the. In this term was a product of two traces. And if we want to make if you want to construct a GLN energy momentum tensor, we should add back this diagonal part, but since that algebra is the usual Heisenberg algebra, we will not have this non-trivial denominator. So if you write GLN current, GLN of the, this will be 1 over 2, 1 over 2, so it will be SLN current. So N of the plus 1 over 2n sum over 1 over 2n, or yeah, 1 over 2n, sum over alpha beta and j alpha alpha of the j beta beta of z. In other words, it is 1/2 sum of j alpha alpha over square root of n squared. So in this, okay. So the difference is that for that the classical level, this algebras are kind of identical, but this quantum corrections which come from central from the combination of central extension and slash constants, make this algebra make these different parts of the energy momentum tensor inequivalent. In a sense, if we had some sum of different non-abelian algebras, we would have the same formulas for this energy momentum tensors, but with different coefficients. It would be not just 1 over 2 2k, but this expression. Because this term was n came from a non-trivial algebra structure. Hmm? Hmm? Because this is the energy momentum tensor for diagonal current. Because if so this diagonal current that corresponds to identity matrix which commutes everything should be sum of j alpha alpha divided by square root of n, because OP of this sum of j alpha 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 over square root of n with itself sum of j beta beta square root of n is precisely 1 over z minus w squared. Because non-trivial OPs appear only between the same alpha and beta. Right? Hmm? Oh, sorry. Yes, you are. Sorry, I wrote it for k equals to 1. Yes, there is a factor of there should be also k here. Yes, thank you. Yes, because it is for some trivial central charge. Yes, so it should be 1 over 2 nk. Mm-hmm. Yes, thanks. So they're different. So in total, this TGLN will equal to. So if I did not make any other mistakes, it should be 1 over 2 k plus n sum over a j alpha beta j beta alpha. So in this difference, what is in this? Probably it will be 1 over k and n plus k. Does it make sense? So if you multiply this, we get k n k n plus k, and in the numerator we have k plus n minus n. So probably like this. Yes. So now let us check if we actually obtain the energy momentum tensor for the free fermions if we do it for GLN. May I read these computations about the Cox number? Hmm? So you have this, we had to obtain this mm, n, and that's all. So k equals 1, free fermions. So there are these formulas for J alpha beta. So let us compute. So here it will be sum of J alpha and beta. So psi star alpha psi beta with mm, no, actually wait. Mm, Let us first think what kind of terms are we interested in. So, mm, first let us write in this expression. So TGLN of D is mm, at level 1 is 1 over 2 k plus n sum of over alpha different from beta j alpha beta j beta alpha plus 1 over 2 1 plus n actually to 1 plus n. We can first write it for generic k. Sum over identical alpha and beta j alpha alpha j alpha alpha. We have this term here and wait, it is with plus sign for some reason. No, maybe it is fine. Hmm? Uh, uh, no, I wanted to write it for a generic key first, but maybe actually, let us actually put it equal to 1 now. So I want to separate terms with identical alphas and betas and with different alphas and betas. And it looks like this, we have such term corresponding for diagonal elements, 1 over 1 plus n. Sum of diagonal elements, and we have another term corresponding to of diagonal elements. So we have such we also have such contribution from this term, which is the same. So we have 2 over so 2 over 2 1 plus n. We have this term, and we also have some term. That hmm? Yes, and another one comes from this combination of JLN and U1 part. And there is also a term 1 over 2, 1 plus n, sum of J alpha alpha, alpha different from beta, J and beta beta. So now let us look at this term J alpha beta. Hmm? Why? Uh, because I missed the factor of 2 somewhere. And so it was originally, and then I missed it. So let us look at this term J alpha beta with J beta alpha in terms of fermions. Hmm? Because I've taken the term where they are the same here. So this term comes from both from two sources. So originally we had sum over alpha and beta here, and sum over alpha and beta here. And then I took the diagonal terms from one sum, from another sum, and wrote them here together. So let us stick with J alpha beta and J beta alpha in terms of the fermions. So it is a psi star of psi star alpha of Z, psi beta of W. So alpha different from beta. Star alpha of Z, psi beta of W, psi beta of Z, psi star alpha of W, psi beta of W. So the LP contains this so there is no OP between I think so there is no non-trivial OPs between this psi's, and we can write it as the normal product of psi star alpha. I'm making some mistake. So it's psi star beta, psi alpha. So it cannot be regular. So there is a term where we pair everything. It is one where z minus w squared. And there are two terms when we pair on these two. It is z minus w, psi beta of z, psi star alpha of w, plus the term where we pair when we pair this. So it is psi star alpha, psi beta of w over z minus w. So psi beta, psi star beta, and psi star alpha, psi alpha. So it is something singular plus d psi beta, psi star beta plus d psi star alpha, psi alpha. Okay, we have this. And actually, wait, I also forgot that there is simply the regular term which comes from normal product of everything, and this term can be written as so it is a normal product of psi star alpha, psi alpha, psi star beta, psi beta. Which is just j alpha times j j beta, j alpha alpha plus j beta beta times j beta beta. Actually, wait, it looks like I made some mistakes somewhere, and that these terms don't want to cancel now. Maybe it is some. Maybe it is some mistake related to the overall sign. It can be even something like this. Hmm? Hmm? Wait, is it like this? So, yes, precisely. So mistake was not before, it was just here. Thank you. Yes, so this term is this. So we are getting here minus this product, which is actually should not write a normal product. It is just a product of two currents that commute. Thanks. So um, and these products we computed them at the moment, but let us do it again probably. So but at least we see that these currents will cancel with this. And this for fermionic currents will not survive. So, and let us see what happens with this term. So J alpha alpha, J alpha alpha, it is psi star alpha of Z, psi alpha of Z, psi star alpha of Z, psi alpha of Z. Actually, we can just use the previous formula for alpha equals to beta. The only difference is that this term will vanish. So, we can write it. Yeah, it was also normally ordered. So we can write it as d psi alpha psi star alpha plus normally ordered plus d psi star alpha psi alpha. So if you take all this together, then we get that T JLN and the level 1 is what? It is sum over alpha different from beta. I'm combining this term with this one and canceling this product. It will be sum 1 over 2n plus 1, sum over alpha different from beta, d psi beta psi star beta plus d psi alpha psi star d psi star alpha psi alpha. This plus 2 over 2 n plus 1 sum of d psi alpha psi star alpha plus d psi star alpha psi alpha. And so probably so so now we see that each one of these terms does not depend on the second index. So we simply write that it is n minus 1 times a single sum. So it is n minus 1 over 2 n plus 1 sum over all alphas d psi alpha psi star alpha plus d psi star alpha psi alpha plus will be just 2 over 2n plus 1 sum of d psi alpha psi star alpha plus d psi star alpha psi alpha. So n minus 1 plus 2 equals to n plus 1, so it is 1/2 sum over alphas d psi star alpha psi alpha plus d psi alpha psi star alpha. Okay, so finally won this battle, and so that the energy momentum tensor, which which was written as quadratic expression of fermions, becomes just a bilinear combination of these fermions. And this happens only if we take into account all degrees of freedom which are present in this theory. In a sense, we should not forget about this diagonal javelin part. So, yeah. Is it okay? And now let us also compute the central charge for this energy momentum tensor in the general situation. For example, yeah, what do you think? What is the central charge for this full energy momentum tensor and for its SLN part at the level 1? So in this situation, we study. No, k equals 1. So, yes. And for SLN. Yes. Exactly. Because we know that if the two operators, if the two parts of theory commute, which is in the case here, because in the Swan current commutes with everything, we don't need to compute this central charge. We can just compute a central charge of the second part, and it is 1. So our overall central charge is n minus 1. But now I would like to derive this n minus 1 from a generic formula for arbitrary weight for arbitrary level k. I want to compute the central charge for a generic value of k. And so probably I don't want to erase these formulas because these computations of the central charge will be similar. So let me maybe erase this computations with the reference. Is it fine for everyone? So far we checked the action of j on this vector L minus 2. But I would like to act with some reverse originators. Maybe to compute central charge, let us first act by L2. So L2 acting on L minus 2 acting on vacuum, it is what? It is C over 12 times 2 times 3 acting on vacuum. So it is n, this is n squared minus 1. So it will be C over 2 acting on vacuum. And we want to do this computation for our case. So we need some formula for L2. Let us remember something. So uh, we would like to act with this we would like to act with this operator on the state given by a kappa sum of j minus 1 squared. So we want to act with this L2 on 1 over 2 k plus h check sum of j a minus 1 squared acting on vacuum. So what kind of terms do we have here? So it is 1 over 2 k plus h check, 1 over 4 k plus h check squared, because we have the same in the definition of the energy momentum tensor. And this O2 terms are near 1 over z to the fourth. Let me first write this terms. So this is sum of j b so sum over b j b minus 1 times j b 3 plus so I'm basically reading this formula and using the fact that if it is L2, then sum of indices should be 2. So plus j b minus 2 j j b 4 plus and so on. But actually, we don't need all this because even this first term acts by zero, because when we try to pull it from ja minus 1 squared, there will be the sum of indices is 1, so we will always have some operator with a positive index that kills this vacuum. So this term does not matter. So and now let us switch to this term. So it is 1. One part of sum, and the second part of sum is j b0, and here it will be j b2 plus j b. So the next term is with 1, b1 j b1. So this looks much more promising. So plus j b0 j b2 plus j b minus 1 j b3. So and this term again has the index 3, so it will kill the state plus something acting on sum of j a minus 1 squared on vacuum. So this term does not enter. This term also ends by 0. This 3 we need to check, and this one starts acting by 0. So let us first act by this. We can immediately say what happens when we try to act with this JB0. So this and this is some generator of non-affine algebra. So a commutator with this is the joint action of this affine algebra, and so it rotates generators in some way, and this combination is invariant on this rotation, so it commutes with sum of ja minus 1 squared and acts by 0 on vacuum. So this term also will also vanish. And so the only remaining terms are these two. So let us commute it with JB1. So it will be sum over AB, JB1, JB1, JA minus 1, JA minus 1, plus JB1, JA minus 1, and this commutator B1, JA minus 1, acting on vacuum. Actually, maybe, I don't know, maybe this could be this still can be done in more rational way. Yes, probably let us do this now without computing all this because mm, mm, yes. Sorry, let us compute at least one part of this in more rational way. Because here we can notice that this is the action of JB one on oh, wait. No, so, mm, yes, so here we have L minus 2 acting on vacuum, and here we have JB1 acting on this state. So we can write the first part like 2 over k plus h check sum over sum over b j b1 j b1 acting on L minus 2 acting on vacuum, right? So we know this action of JB1. Mm. And the next part, let me think, probably it cannot be simplified like this. Mm. Only if we represent JB2 as a commutator of something. But let us not try to do this. So let us simply write and the term is this. So it is 1 over 4k plus h check jb0 jb2 ah, let us compute this commutator. So it will be jb0 f b sum over a f b a c j j it will be fb a c j b 0 j c 1 j a minus 1 plus j a minus 1 j c 1 acting vacuum. Is this fine? So then we can so first we do something with this term, namely we remember that it is so this equals to j B minus 1 acting on a vacuum. So we write it as 1 over 2 K plus H check sum over B and J and B1 and J and B minus 1 acting on vacuum. And in this term, I would like to antisymmetrize these expressions because they appear together with this structure constant. So mm, hmm? Yes, thank you. Yes, it vanishes because it acts on a vacuum. And for this piece, we need again to commute them, and um, this part with zero index will vanish. Um, mm, so no, will it vanish? Yes, it should vanish. And uh, hmm? mm, Let me think. Yes, but it contains JB0, so it should also vanish. So, okay, I forgot. Actually, this term does not contribute at all. And so this acts by zero, and we are left with this term. And here we need to compute the commutator, which is mm, again zero part will act by zero. And this commutator that contains a central extension will give a k over 2k plus h check sum over um, ones or b acting on zero. And so it is sum of all generators of our group. So it is or our algebra. So it gives the dimension of this algebra. So it is k times a dimension of G. Actually, I did not introduce any notation for this algebra, but what is noted like this. The dimension of G times over K plus H check. So and this is a C over 2. So C equals to K dimension of G over K plus H check. So examples. Uh, hmm? Hmm? But no, mm, uh, 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 because JB0 is the generator of non-affine algebra, and we know from these commutation relations from these commutation relations that terms with zero index act in the adjoint way, and they rotate basis of this algebra independently on n. So it is just Hmm. Uh, the action of non-affine algebra on the affine algebra, and this expression, a sum of squares of this of all generators, is invariant under such rotation. So yeah, this JB0 commutes with the sum of J minus 1 squared because it does not have an algebra index. It is some invariant of invariant under the action of non-affine algebra. Uh, and then so it commutes with this, and then it acts by acts on vacuum. Vacuum is invariant under the action of this algebra. So examples. So let us check this example we already computed. Uh, C equals SLN. And dimension of G is n squared minus 1. H check is n. Central charge is n squared minus 1. K equals to 1. Central charge is n squared minus 1 divided by n plus 1 is n minus 1. Right? So SO2 at arbitrary level. So it is a SLN 1, SO2 at with arbitrary level K. So a dimension of algebra is 3. So C equals to 3K over K plus 2. And then there are options. One option is C is K equals to 1, as we had before. So, K equals to 1, C equals to 2. Oh, sorry, no. Oh, did I? C equals to 1. So we will see probably the next time that this C equals to 1 is actually the same C equals to 1 as for the Frege boson. There is actually we can say it even now because it is a representation in terms of n complex fermions, but we can bosonize all these fermions, and in this way we can get a representation in terms of n free bosons. So this off-diagonal currents will be given by some exponentials, and diagonal currents will be just defies. And then we remove one diagonal boson, so this way we get C equals n minus 1. And here we can just write everything in terms of a single boson. But here there is also another funny case, namely we can consider K equals 2. So central charge in this case is 3 over 2. So what do you think? What can this central charge correspond to? Mm. Yes, such representation also exists, but there is a more straightforward option, like and spin. No, maybe it's too much. And the central charge is not proportional to spin. It's not the function of spin. Oh, one real fermion and one boson is one possible option, but it's more complicated. The most naive option is to say that SO2 is isomorphic to SO3. SO2 is SO3. And since it is so, remember that there is a realization of orthogonal groups in terms of in terms of real fermions. There are operators J alpha beta equals to psi alpha psi beta with alpha beta from 1 to 3. 1 to 3. And if you want to write it in terms of boson, you can say that there are different indices. So it is one option. Another option is to say that alpha beta are one bar and 0, 1 and 1 bar. 0, 1, and 1 bar. In this case, these generators will be J. So these J's will be psi 0, psi 0, psi, psi 0, psi star, and psi star, or psi star psi. Psi star psi. So this is the real fermion psi 0, and this psi and psi star are complex fermions. These complex fermions can be bosonized. So in this way, there will be this strange realization of SO3 in terms of real, in terms of boson and one real fermion. So this current will be d phi, and these two currents will be exponentials times fermion. So in a sense, you can combine all possible transformations between free fields and get different realizations of different algebras. Mm. And so, and this should also correspond to in k equals 1 a realization of SO. So it should correspond to k equals 1 for SO3, I think. Oh, or not. No. No, the Opus number is the same, so no, it is k equals 2 still. Actually, there is one one other isomorphism, or maybe even I know there are two other isomorphisms between different linear groups and orthogonal groups. And actually, I didn't think about such relations, but let us try to see this now. Maybe no, maybe we will not see anything interesting. Principle, there are isomorphism between so this is isomorphic to this Linkin diagram, and this corresponds to isomorphism between SL4 and SO6, and there is this isomorphism between well between SO2 times between SO4 and SO2 times SO2. Oh, in this case plus, if you write it for the algebras, but I don't know if there is such isomorphism, if there are such coincidences between the central charges. But well, in principle, it should be, because there is a fermionic representation here, which should correspond to c equals to 3, and there should be so, and here fermionic representation. Well, no, here it is also c equals to 3. Because here it is for complex fermions without one boson, and here it will be 6 real fermions. So it is the same, nothing interesting. I just thought that if we have any other relations of this kind, I probably know. I can't remember this. So, and what else can we say about this? We can also think what happens when we send this level of this algebra of this affine algebra to infinity. We see that in this case k and k plus h check become the same, which means that this algebra looks like free fields of the number that equals to the dimension of this algebra. So it's a kind of one possible classification. So another option is to consider k equals to minus h check. So in this case, we will need to renormalize this energy momentum tensor. So if we consider k minus h k plus h check times energy momentum tensor, and denote it with denoted by t tilde. Then the OP of this t tilde with t tilde will equal to k plus h check squared times c over 2 over z minus w to the fourth plus k plus h check times t of z plus t of w over z minus w squared t tilde plus. So we can write then that t tilde with tilde equals to k plus h check something like c tilde over 2 z minus w to the fourth plus t tilde of z plus t tilde of w over z minus w squared. So so we say then k goes to minus h check. So we see that the OP of t tilde with t tilde becomes regular. In a sense, this in a sense, modes of this t start to commute, but we have some formula like commutator of some L n L m becomes proportional to k plus h check, which goes to 0. So it is a kind of transition to Poisson vertex algebra. So in a sense that we will have some Poisson bracket instead of commutator. So. So. Mm-hmm. Oh, a singular part is proportional to commutator. It defines commutation properties. So yes, if we rescale t in this way, then this algebra becomes commutative. So if you use the old definition of t, it becomes singular. So it is natural to consider just this sum of j squared over 2 and say that it is our new field. So at this critical level, this field becomes commuting. So we have some algebra of functions on some infinite dimensional space. In the sense, this J's can be interpreted as a function on something, basically on a spectrum of a ring generated by all these J's, and they commute. And this algebra is supplied by Poisson bracket, which is the first correction in this product, or maybe we can say that if some commutator in some algebra goes to 0, and with that k plus h check, we can call this a Planck constant and say that coefficient in front of it is a Poisson bracket. So we can write, so we will have something like Ln n with Lm equal to 0. But at the same time, we will have Poisson bracket of Ln and Lm, which is basically the same as before. C over 1 over 12. Oh, some constant. C tilde over 12 n squared n cubed minus n delta n minus m plus n minus m l n plus m. So it's the classical limit when c is minus 2. Are there any questions about this? Okay, if no, then maybe thanks for your attention. See you on the next week.